For the first part of part D, we're going to be starting with our process transfer function, which is our GP, and we're going to be simulating this and then adding some normally distributed random noise in order to simulate getting some real data. So we will take our function we already know, and then we will add random noise in order to simulate data. So the first thing we need to do is we need to simulate our function. We have scipy.optimize import minimize for later when we calculate the sum squared error to get a better fit for our k and tau values. But for now we can ignore that. So our time and our y values will be equal to our simulation of our transfer function, and t. We'll use a time step of 1.2. We'll do 50 different points, and we'll have the time change of 2.5. So now what we can do is plot this out. So our figure be make subplots fig dot add scatter our x equals t, y equals y. Our mode is going to be markers, and we'll call this our name GP. So as you can see, this is just almost exactly straight lines, and there's no randomness at all. So what we can do now is add a little bit of randomness artificially. So our y is equal to our np.random normal of our y, and we'll add with the standard deviation of 0.05. And now you can see there is a little bit of error, or not error, but just randomness going on, making it closer to what a real set of data would look like. For the next part of homework 4, we're going to be fitting our data to a first order plus time delay model, and by doing this we will be able to then generate a line of best fit by minimizing our sum squared error of our synthetic data. So we'll define our first order plus time delay model as a function of time, our k values, our tau, and our theta, which this is going to return our np dot what is this? Why can't I remember? np.where our time is greater than theta, which will simulate our time delay, our k value multiplied by 1 minus np.exp of our negative t minus theta divided by our tau, and then finishing out our arguments for np.where, they're 0. From this, we'll then need to define our sum squared error function. So we'll define our SSE as a vector, which will give us Ka, tau, and theta, which will be unpacked from B, where we will return np.sum of our y data, so y minus FOPTD of our time, our Ka, our tau, and our theta. And this will be squared, giving us our sum squared error. And now our Ka value, our tau, and our theta will be equal to our minimize function of our SSE with the initial values of 1.8, 30, 15, and we'll see what this does. Minimize. Did I spell minimize wrong? Too many values to unpack. We only want our solutions when it converges, so we only want to unpack our x's of the minimize function. So now if we want to look at our Ka, our tau, and our theta, we will get the values that it decides are best for fitting a line to our function. So we can now add these by getting another plot here. So figure.add scatter. We want this to be lines. Can I move this? Move down, 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 down. Okay. And then we'll make our y model equal to FOPTD of our time, our Ka, our tau, and our theta. And as you can see, it matches up pretty well. Oh, this is just our y value. We want y model. If I could spell model right. There we go. Our best fit line to our synthetically generated data. For the last part of homework 4, part D, we're going to be starting with our parameters from our Smith and Corpio table from a set point change, which will give us a controller that will work best for our system. So the first thing we need is our K, which is just going to be equal to our Ka, which we determined from our sum squared error, divided by our time delay. We need our Y, which is going to be equal to our PA multiplied by our theta and tau we calculated from our sum squared error, which will be to the power of our PB. We then have our Kc value, which is going to be equal to our Y divided by K, and then our tau I, which is going to be tau divided by our IA plus IB multiplied by theta divided by tau. And from this, we can then move on to make our GC, which is going to be equal to our Kc times 1 plus 1 over tau I times S plus 1. We don't need our GP because it's already defined, and we don't need that plus 1 there. So our GCL, our closed loop, is going to be equal to our controller gain, GC, times GP, using our shortcut. And we know that this will be divided by everything up there again, just plus 1, GC times GP. And then again, we didn't run this yet. We will simulate this one more time. Our T and our Y controller, Y controlled. Our simulation, our GCL, lambda T 1.2. We'll do this for more time steps and a smaller time between each one. And then we can take a look at this. So figure 3, fig 2, make subplats fig 2 dot add scatter. Our x values will be RT. We'll call this T2 just not to make them overlap with anything from above. T2. T Y is equal to our Y controller mode is equal to lines, and our name will be GCL. Close it. Gotta run this, and you can see our system is stable, and that is simulating a set point change and our time delay. And we make our time steps a little longer. We can see that our controller works, getting us back to our set point of 1. And as we change what we want our number to be at, we can see our system will eventually steady out at what we need it to be at. So if we increase it to 2, it still reaches a steady state because we were able to use our fitted line from our sum squared error, and then using our Smith and Corpio values determine a controller value and a gain that would be effective but also not overshoot and become unstable.